Welcome to This Explainer. Today we're diving into a complete explanation to uncover the secrets and narrate the hard, evidence-based facts behind the universe's absolute most enigmatic structures. We are going deep. So what happens when matter gets so dense that literally nothing, not even light, can escape? Picture this terrifying, unstoppable force. We're talking about cosmic vacuum cleaners that pull in absolutely everything that crosses their path, completely breaking the known rules of physics in the process. How does any place in the universe even reach that extreme level of density? Well, that's exactly what we're going to find out. All right, part one, the universe's mystery, and figuring out what exactly the whole even is. To really get this, we have to look at the massive shift in how we understand physics. For the longest time, we looked at gravity purely through Isaac Newton's eyes. A straightforward pulling force, like an apple falling from a tree to the earth. Simple enough, right? But then, Albert Einstein comes along with general relativity and totally flips the script. Imagine the universe not as empty space, but as a stretched-out, flexible fabric, kind of like a trampoline. Now, drop a heavy bowling ball right in the center. The fabric stretches, it curves, it warps all around that heavy mass. And that's exactly what massive objects do to the actual fabric of space and time. We call it space-time. And we can actually see this happening. When you have an incredibly massive object sitting right in the center, it acts just like a giant magnifying glass. The extreme mass warps space-time so intensely that it physically bends the path of the light traveling from the galaxies sitting directly behind it. This is called gravitational lensing. It literally distorts reality right before our eyes, giving us absolute, undeniable proof that Einstein's warped spacetime is completely real. Okay, moving on to section 2, the birth of black holes and the different types out there. Let's break down the violent chain of events that actually creates one of these things. At its core, a star is just a giant ball of hydrogen. So in step 1, nuclear fusion inside the core converts that hydrogen into helium, generating this immense outward energy that constantly fights against the crushing weight of gravity. It's a cosmic tug of war. But in step 2, the fuel inevitably runs out and gravity finally wins. The star violently explodes in a massive supernova. Then, in step 3, the leftover core just collapses inward on itself under its own unbelievable weight. It's an absolute unstoppable catastrophe that forges a stellar mass black hole. Now, to really wrap your head around the sheer insanity of this collapse, we have to talk about density. If you were to scoop up just one single teaspoon of this collapsed matter, well, it would weigh over 400 billion tons right here on Earth. Just let that sink in for a second. 400 billion tons in a teaspoon. It's a staggering number that really drives home the fact that we're dealing with an extreme state of matter unlike anything else. Which brings us to section 3. Anatomy of the whole, properties and secrets. Now here is where it gets kind of weird. Despite their infinite complexity and all the crazy mystery surrounding them, a black hole can be defined entirely by just 3 simple properties. First, its mass, which dictates its size and gravitational pull. Second, its spin, or angular momentum, which it basically inherits from the dying star it used to be. And third, its electrical charge. That's it. Everything else, all the specific details about whatever fell inside, is completely erased and hidden forever from the outside universe. When we look at the structure itself, there's a very specific outer boundary. We call it the event horizon. Make no mistake, this is the absolute point of no return. The exact second anything, even light, crosses this threshold, it's trapped for good. And if you go right down to the very center, you hit the singularity. This is where all that mind-blowing mass is crushed into an infinitely small, infinitely dense point. Right there, at that exact spot, the laws of physics as we know them, they completely break down. They just stop working entirely. Let's look at the hard facts in section 4, uncovering the hidden, observational evidence. The crazy thing is, our trail of evidence started out purely as math. Way back in 1916, Einstein's equations predicted these things on paper, but it took decades to go from theoretical math to hard observational proof. The 1960s really changed the game here. In '63, Martin Schmidt discovered quasars, which were pouring out unbelievable amounts of energy. And then in '67, Jocelyn Bell spotted pulsars emitting these super precise radio pulses. These discoveries were totally undeniable proof that super dense, gravity warping anomalies were out there lurking in the dark. Because absolutely no light escapes, we can't actually see the black hole itself. But we can see the violent chaos happening right outside of it. When a black hole feeds on nearby matter, It whips all that gas and dust into a superheated, swirling frenzy called an accretion disk. The friction and magnetic fields get so intense that it violently ejects massive jets of radiation outward at nearly the speed of light. So we're not seeing the dark sphere itself. We're basically watching its very messy meal. But to capture these crazy, powerful emissions, human eyes just aren't going to cut it. We have to rely on massive arrays of radio telescopes. These arrays sit and stare patiently into the cosmos, acting as our investigative senses to capture those hidden interactions and invisible radiation. This is the solid, undisputed proof we gather to confirm these monsters are truly roaming out there between the galaxies. Actually, here's a totally wild fun fact you probably didn't expect in an astrophysics explainer. The search for these hidden anomalies directly changed our daily lives. Seriously, the complex algorithms created by an engineer named John O'Sullivan, which were originally designed to filter out background noise while hunting for radio waves from exploding black holes, were later used to invent the 802.11 protocol. That is literally the foundation of modern Wi-Fi, the very same Wi-Fi you're probably using to stream this right now. It just goes to show how incredibly interconnected science really is. All right, on to our final chapter, Section 5, Hawking Radiation and the End of Holes. So we know how they're born, and we know how to observe their effects. But the big question is, do they live forever? This brings us to the legendary physicist Stephen Hawking, who made a truly brilliant deduction. Looking at it through the lens of quantum mechanics, black holes aren't actually 100% black. They emit this tiny, incredibly faint trickle of thermal energy, which we now call Hawking radiation. And because they leak this radiation, they are slowly, almost imperceptibly, losing their mass over time. Let's break down exactly how this happens at the quantum level. Right at the very edge of the event horizon, pairs of virtual particles are constantly popping into existence out of nowhere. Occasionally, one of those particles, the one carrying negative energy, falls into the black hole, while its partner escapes as positive energy. That negative energy essentially subtracts from the black hole's overall mass. Over trillions and trillions of years, as the surrounding universe cools down, this process accelerates, causing these giant cosmic entities to quietly, eventually evaporate into absolute nothingness. Which leaves us with a pretty profound thought to wrap things up. We've walked through the hard, evidence-based facts, from the dramatic warping of space-time to their eventual inevitable evaporation. But when that incredibly distant, unimaginable future finally arrives, and the very last black hole fades away into the dark, what exactly will be left? Will that be the true end of everything? It's a question that really leaves you in absolute awe of just how mysterious our universe is. Thank you so much for joining me in this explainer, and as always, stay curious.